Astronomers use the term apparent magnitude to describe how bright an object appears in the sky from Earth. The idea of a magnitude scale dates back to Hipparchus around 150 BC, who invented a scale to describe the brightness of the stars he could see. He assigned an apparent magnitude of 1 to the brightest stars in the sky, and he gave the dumbest stars he could see an apparent magnitude of 6. He did not include the sun or moon in his system. The magnitude scale astronomers use today is based on Hipparchus' system, but has been expanded since the invention of the telescope. In this system, the brighter an object appears, the lower its magnitude. Some of the brightest objects visible in the sky, including the sun, have negative values for apparent magnitude. Our eyes can detect about a factor of 100 difference in brightness among stars, so a first magnitude star is about 100 times brighter than a sixth magnitude star. We have preserved this relationship in the modern magnitude scale, so for every 5 magnitudes of difference in the brightness of two objects, the objects differ by a factor of 100 in apparent brightness. Surface photometry of galaxies is a technique to quantitatively describe the light distribution of the galaxies, as recorded in two-dimensional images. Surface photometry is used to study extended objects, such as galaxies, as opposed to point sources, such as stars. From an image of a point source, only its total magnitude can be derived. From an image of a galaxy, it is possible to determine a number of quantities. Some of these quantities are derived from surface photometry, such as how the intensity and ellipticity vary with radius. Surface photometry of galaxies has undergone a great advance recently with the development of fast digital plate measuring machines, powerful computers to process the huge amount of data from them, and efficient image processing software. Further, the recent advent of charge-coupled devices (CCDs) has made the technique effective even with relatively small telescopes. Because of their very high sensitivity, especially in the red wavelength region, CCDs have opened the new era of surface photometry. We describe galaxy surface photometry based on fitting ellipses to the isophotes of the galaxies. For example, galaxies with different isophotal shapes are used to illustrate the process, including how the deviations from elliptical isophotes are quantified using Fourier expansions. Today we know that galaxies are as common as blades of grass in a meadow. Telescopes recently completed a particularly deep faint census of a tiny pencil beam extending far out into the universe. This survey, called the Hubble Deep Field, was targeted on a region of the sky that was nearly devoid of known objects, so as to be hopefully representative of conditions in the distant universe. The resulting images are truly amazing. Strewn across this tiny piece of the sky are perhaps 1,500 or more galaxies of all shapes, sizes, and colors. Because this survey pertains to such a small piece of the sky, the implications are staggering. If the region of sky demarked by the bowl of the Big Dipper were surveyed to the same depth, it would contain about 32 million galaxies. And the estimate for the entire visible universe is that there are upwards of 40 billion galaxies. The most common type of galaxy is called a spiral galaxy. Not surprisingly, spiral galaxies look like spirals, with long arms winding toward a bright bulge at the center. But be careful, if you looked at a spiral galaxy from the side, you could mistake its shape for a circle, and so you'd have to use other criteria to learn it was a spiral. If you can't clearly see the spiral shape, the galaxy is called a face-on spiral. If you instead see the galaxy from the side, it is called an edge-on spiral. You can recognize edge-on spiral galaxies because you can see their bright central bulges. Face-on and edge-on spiral galaxies aren't really any different, they only look different because of the angle from which you see them. Some spiral galaxies have arms that are wound tightly, while other galaxies have very loosely wound arms. The difference between tightly and loosely wound spirals is a genuine difference between the galaxies, and can be used to classify spirals. Spiral galaxies are further classified by how tightly their spiral arms are wound. Most of the galaxies that scientists have discovered so far are spiral galaxies, as opposed to the other two main categories of galaxy shapes, elliptical and irregular. Spiral galaxies make up roughly 72% of the galaxies that scientists have observed. M31 is the brightest galaxy you can see. You can see M31, also called the Andromeda Galaxy, for at least part of every night, all year long. but most people see the galaxy first around northern autumn, when it's high enough in the sky to be seen from nightfall until daybreak. The visible fuzzy patch stretches about as long as the width of the full moon, and half as white. Only with significant magnification can you tell it stretches 6 times that length in fullness. When Charles Messier labeled it M31 in 1764, he incorrectly credited the discovery of what was then called a nebula to the German astronomer, Simon Marius, who provided the first telescopic observation of the object. The first photographs of Andromeda were taken in 1887, by Isaac Roberts. In the 1930s, Karl Jansky, the physicist with Bell Telephone Laboratories, discovered that the static interference on transatlantic phone lines was coming from the Milky Way. By the 1950s, astronomers were using radio telescopes to probe the heavens, and pairing their signals with visible examinations of the heavens. Quasars. Astronomers first knew they had the mystery on their hands in the 1960s. Then they turned the first radio telescopes to the sky. They detected the radio waves streaming off the Sun, the Milky Way and a few stars, but they also turned up bizarre objects they couldn't explain. These objects were small and incredibly bright. They named them quasi-stellar objects or quasars and then began to argue about what might be causing them. By 1965 it was recognized that quasars are part of a much larger population of unusually blue sources and that most of these are much weaker radio sources too faint to have been detected in the early radio surveys. This larger population, sharing all quasar properties except extreme radioluminosity, became known as quasi-stellar objects or simply QSOs. Since the early 1980s, most astronomers have regarded QSOs as the high-luminosity variety of an even larger population of active galactic nuclei, or AGNs. The lower luminosity AGNs are known as Seyfert galaxies, named after the American astronomer Carl K. Seyfert. Some quasars are also observed to have radio jets, which are highly collimated beams of plasma propelled out along the rotation axis of the accretion disk at speeds often approaching that of light. These jets emit beams of radiation that can be observed at X-ray and radio wavelengths and less often at optical wavelengths. Because of this complex structure, the appearance of a quasar depends on the orientation of the rotation axis of the accretion disk relative to the observer's line of sight. In addition to studying the quasars themselves, many astronomers use quasars as background light sources to study the intervening galaxies and diffuse gas. This is referred to as absorption spectroscopy because the intervening material is detected only because it absorbs some of the quasar's light as it travels to Earth. Quasars are ideal for this purpose since they are very compact point sources quasi-stellar on the sky and are so bright that they can be seen through telescopes at enormous distances. Indeed, quasars are among the most distant objects known. They therefore allow astronomers to study details of distant galaxies far too faint to be seen directly. As celestial phenomena go, comets are impressive, bright blotches of light with long, beautiful tails, suddenly appearing to blaze across the sky before fading away just as unexpectedly as they arrived. Though frequently beautiful, comets traditionally have stricken error as often as they have generated wonder as they arc across the sky during their passages. Astrologers interpreted the sudden appearances of the glowing visitors as ill omens presaging famine, flood or the death of kings. Even as recently as the 1910 appearance of Halley's Comet, entrepreneurs did a brisk business selling gas masks to people who feared Earth passage through the comet's tail. A comet is a very small body made mostly of ices mixed with smaller amounts of dust and rock. Most comets are no larger than a few kilometers across. The main body of the comet is called the nucleus, and it can contain water, methane, nitrogen and other ices. The primary part of a comet known as the nucleus is a mixture of mostly ice, bits of rock, dust and other frozen gases. As comets approach the Sun, radiation begins to vaporize their frozen gases and ice, creating a cloudy glow around the object. Known formally as the coma. The other distinctive part of a comet is the tail area. Radiation pressure from the Sun pushes material away from the comet, forming two tails. The first tail is the dust tail, while the second is the plasma tail, made up of gas that has been evaporated from the nucleus and energized by interactions with the solar wind. The first spectroscopic observations of comets were made by Giovanni Donati 1864 and by Sir William Huggins 1868, who visually compared the spectrum of comet Winnetka 1868 with flame spectrum and found that the bands seen in the comet and in the flame, now known as the carbon or swan bands, were similar. Subsequent observations showed that these bands were present in all comet spectra and that carbon was therefore an important constituent of comets. Spectroscopy pertains to the dispersion of an object's light into its component colors. Only through studying astronomical objects at many different wavelengths are astronomers able to piece together a coherent, comprehensive picture. Techniques may be grouped according to the type of radiative energy, like electromagnetic radiation, acoustic pressure waves, particles such as electrons, the type of material being studied like atoms, crystals, molecules, atomic nuclei, the interaction between the material and the energy like emission, absorption, elastic scattering, or specific applications. Modern spectroscopy uses diffraction gratings to disperse the light, which is then projected onto CCDs, charge-coupled devices similar to those used in digital cameras. The two-dimensional spectra are easily extracted from this digital format and manipulated to produce one-dimensional spectra. Peak offers optical and infrared spectroscopy on May-alpha-meter, WIYN, 2.1 meter, and Coupe feed telescopes. Each instrument telescope combination has advantages and capabilities overlap. The Mauna Kea Spectroscopic Explorer is a planned 11.25 meter, wide field, optical and near-infrared facility completely dedicated to multi-object spectroscopy of samples of between thousands and millions of astrophysical objects.